Hello, my name is Yahel Valdez-Rodriguez. Today I will present to lab number 3. My partners are Braulio, Silva and Samatha Arellano. For our introduction today, in today's lab we will use gravity as a constant force to generate this kind of movement. We can use this outside the lab by using an engineering design as shown here, where precise motion measurements can help build safer vehicles, machines, and structures. Our materials today will be an air glider. We've used an air glider in labs number 1 and 2. We'll keep using it today. We will keep using the capsule motion sensor in order to detect our position, velocity, and acceleration, as we will use 3 graphs, and our capsule software as we record our graphs, like we always did, like in lab number 1 and lab number 2. Here is a video of me looking at the graphs and how everything is going to be measured. This is the start of the lab, so we're trying to figure out how to manipulate the air glider into work into the graph. Not much information is shown, but as you can see, we're trying to still keep on moving forward. In this video, as you can see, it's me and Braulio Silva. We're trying to conduct an air glider now, and as you can see, we have 2 graphs right here. Our first one is our position, and our second one is our velocity. As you can see, here we're demonstrating how to do the graphs and the air glider moving smoothly, as you can see, throughout the air glider table. This is your graphs, and for the first graph, as you can see, we have 3 different types of graphs. As you can see, in this one, we have the position time graph, which is in green. We've seen a set of valleys, as you can see, and they're rounded, compared to our velocity, which turns into the slope of the position. As you can see, it's like a piked graph, and our acceleration is like a stutter pike graph, which is the slope of the velocity. As you can see in the second graph, we see that we close into our graphs, and we're trying to measure our position for the velocity from one point of velocity to another, as we did in the first graph and the second graph and the third graph. All of them are zoomed in, and we're trying to measure which points to use, as all 3 are shown in this slide. Here we conducted our results on our data. For example, our MW times our gravity. Our MW was 195 grams times the gravity, which is 9.8. Eventually, we got 244.02. And for our MW plus MC, which is the 195.5, which is the weight of the air glider, we measured the grams, and we measured the little gram on the air glider, which added them up, which was 244.02 divided by 220.4, which would equal negative 1.1, and our theoretical acceleration was negative 1.1. Here we see that our acceleration, we're trying to use our position versus time graph, collect data on the glide going from the steady position to reach the end of the track, scale your graph to see how the movement, repeat the measurement until you have a smooth curve. As you can see right here, we have the equation for acceleration, which is our final velocity minus the initial velocity, or the final time minus the initial time. So our data process, which was step number 1, was we had to start using our position versus time graph. We needed to use 2 points at the beginning of the movement to calculate the initial velocity, as I showed you right in the graphs, like in the previous slide. We had to use also the multi-coordinate tool to select the points and make necessary annotations, like in the last slide, as I mentioned before. So here in table 2, we had the values to calculate the initial and final velocity. Points needed to compare initial velocity. Position number 1 was 1.06 meters, and our time was 2.7 seconds, and our position change was 0.4 meters. For position 2, it was 1.05 meters. Our time 2 was 2.75 seconds, and our time change was 0.05 seconds. It resulted in an initial velocity of negative 0.2 meters per second. Our points needed to compare final velocity, which was a position number 3 as shown, was 0.61 meters. Our time 3 was 3.55 seconds. Position change was 0.05 meters. And our position 4 was 0.536 meters. Time 4 was 3.6 seconds, and our time change was 0.05 seconds, resulting in a final velocity of 4 meters per second. Our step 2 was using our velocity calculated values and the times in the highlighted cells in order to get our acceleration number 1. For example, right here in our acceleration number 1, as we used previously in our numbers, we ended up calculating a negative 0.8 meters per second squared. In the capstone, we had to choose a velocity as a measurement for this graph. We had to choose an initial and velocity point to compute what we call acceleration. We use this, as I mentioned before, 2 points from the position and velocity graphs. So, in order for that to happen, we use our table here, which is the velocity values in acceleration 2. And velocity number 1, we had a 0.0 meters per second squared on acceleration. And we have velocity 2 at negative 0.99 meters per second squared. Our velocity change was a negative 0.89. For example, time 1 number 1 was 2.7 seconds, and our time 2 was 3.6 seconds, and our time change was 0.9 seconds, resulting in acceleration 2 of being 1.1 meters per second squared. Finally, in a new page icon, we chose an acceleration as a measurement. As you can see, we had to choose 2 points for each graph, which was the position, velocity, and acceleration graphs, which resulted in us getting an acceleration of 3, making it seem like a negative 1.03 meters per second squared as our third acceleration. Finally, we had to experiment our percentage of error, which was the theoretical value minus the experimental value over the theoretical value, times 100. And here in table number 5, we have our percent errors. In acceleration number 1, we had a 37.5%. Our acceleration 2, we had a 0.0%. And our acceleration 3 had a 6.75% error. Finally, for our credits in this lab was on camera was me and Braulio, as shown in the videos I've showed you before. Who did the calculations was Samatha, Arellano, and Braulio Silva. Carried out the experiment was Samatha, Arellano, Braulio Silva, and myself, and the editing for this video was me. In summary, as shown here, should these percent errors be similar or not? Why? We put that yeah because of the fact that they would have to be lower or close to 10%. Where does the error come from? The error came from either a software issue or we applied the wrong points on the graph. Can or should this error be precisely 0? Yes, it can. It happened in acceleration number 2, as I showed you back in the table. We considered it to be a good experiment for this type, and we would calculate the acceleration by using the final velocity minus the initial velocity divided by time, and that's the method we would choose for acceleration. Thank you so much. I'm Yahel Valdez. My partners were Silva and Samatha Arellano, and I'll see you in the next lab.